today's experiment, we're going to measure the mechanical equivalent of heat. And it's a very interesting way of doing it. You generate heat when two surfaces rub together. So we have this rope here, which is going to wrap around this cylinder. Okay? And we're going to turn this crank. I'm going to get several turns on the rope here. And as I turn this crank, it levitates the bucket. So you can see the bucket is lifted off the ground right now. But then if you look at the crank and the cylinder now, as I spin this, you can see that the rope is not moving, it's slipping and providing a rubbing friction onto the cylinder. Now that's going to heat the cylinder up, that friction. So as I turn this crank here, there's a certain amount of frictional force on the edge of the cylinder. And that force is rubbing in an equal amount to the friction force that's going the other way, and that's going to heat up the cylinder. So if we have a way of measuring the temperature of the cylinder, and we know the specific heat of the cylinder, we can see how much energy is being poured into the cylinder and heating it up. And then I can compare that number to the actual work I'm doing to spin the crank. And by comparing those two numbers, this work I'm doing to turn the crank with my hand, I have to push, so I'm doing work. That work I'm doing is going to be equal to the heat that gets dumped into the cylinder and raises its temperature. So if I know the specific heat of the cylinder, it's made out of aluminum, I know its specific heat, I can determine whether or not the amount of work that's being done is equal to the amount of heat that goes into the cylinder. Now, in order to determine the amount of heat that goes into the cylinder, we're going to measure its change in temperature. And as you can see, we have the cylinder itself has some electromechanical leads connected to it, which go to an ohm meter. And the actual resistance of the reading on the ohm meter can be converted into the temperature of the cylinder by this table right here. So you can see there at 95,447 ohms, that's this number right here. That's 95.447 kilo ohms. That's a temperature of 26 degrees. Now, in the table, the column to the left of that, you can see that 269,080 ohms, or 296.080 kilo ohms, corresponds to 5 degrees Celsius. So it's a semiconductor thermometer. As the temperature goes up, the resistance in ohms goes down. So that's going to enable us to measure the temperature of the cylinder. Now, if I spin this off here, if I take this and spin it off, let me show you how I'll do that. I can spin this off of here. And pull the cylinder off. And look at the cylinder. You can see this ring here. The resistance is between this point, between the inner and outer points of the ring. That's a semiconductor material. So you're actually measuring the resistance between here and here. And that resistance of that embedded semiconductor material is going to tell us the temperature of that semiconductor material, which is in thermal contact with all the aluminum around it. All the aluminum around it. And so that's going to give me the resistance, electrical resistance between this outer edge and this inner edge is going to give me the resistance of that material, which is an annular cylindrical ring down here. And that resistance will tell me the temperature of the aluminum. Okay? And it's calibrated. It's all calibrated by this table right here, which is actually on the side of the apparatus. Okay, now the theory for the experiment is that this cylinder is here, and you have this rope wrapped around it, and at the end of the rope is a 10 kilogram bucket of sand, or it's actually a paint can filled with sand. And so in this scenario, the force of gravity on the 10 kilogram bucket is this mg. There's a tension in the rope, and that same tension in the rope is this way at the top of the cylinder, and the radius of the cylinder is this r here. So there's a torque on the cylinder that's as the rope slips and the cylinder spins, and the torque is the radius of the cylinder times the force at the edge of the cylinder. That's the torque. And that's going to be equal to the torque. Now this T here is the tension in the rope. And the tension in the rope is mg, where M is the 10 kilogram paint can filled with sand, okay? So the work done for every turn of the crank, the work is the integral of the torque d theta, which is going to end up being equal to, for every turn of the crank, you get theta is 2 pi. And if you, let's say you go around twice, that'll be 4 pi. 3 turns of the crank will be 6 pi. So the number of turns. And then the torque is going to be the tension, which is mg, times the radius of the cylinder. So this equation here is the mechanical work that's done as I turn the crank and that rope slips on the cylinder. That's the mechanical work. And that number, so mgr times 2 pi n is, if that mechanical work gets converted to heat and heating up the cylinder, that should be equal to the mass of the cylinder times the specific heat of the cylinder times the change in temperature, the final temperature minus the initial temperature of the cylinder. And so this is the theory that we'll be testing. On the left-hand side of that equation is the mechanical work that is done when you spin the crank n turns. And the right-hand side of the equation is the heat that goes into the cylinder. The mass of the cylinder times the specific heat of the cylinder. That's this number C, CYL. That's the specific heat of the cylinder times the final difference in temperatures of the cylinder. So this is the theory that we will be testing right here. Again, the left-hand side of the equation is the mechanical work. And is that equal to the heat that goes into the cylinder? And we're going to measure this directly. Now, what's going to happen as we have this on here, and the rope is slipping on the surface of this, is, if the room is hotter, as you know, heat flows from hot to cold. So if the room is hotter than the cylinder, the room will actually add heat to the cylinder. And then as the cylinder gets hotter than the room, the cylinder will lose heat to the room. And this will create error in your experiment. So what we want to do is we want to cool the cylinder down below the temperature of the room. Right now the temperature of the room is about 17, 18 degrees C. Okay. So what we want to do is cool down the temperature of the room. we want to cool down the cylinder so it's colder than the room for half the experiment. And then for the other half of the experiment, we want the cylinder hotter than the room. So if we take this down to, if the room, say, is 18 degrees Celsius right now, and we lower the temperature of the cylinder to 10 degrees Celsius before we start the experiment, then the room will be adding heat to the cylinder, and that's a source of error because that's not generated from the friction. But then for the other half of the experiment, in other words, if we start this at 8 degrees Celsius and take it up to 28, then for half the time the cylinder is colder than the room. The room's at 18 degrees Celsius. And for the other half of the time, from 18 degrees Celsius to 28 degrees Celsius, the cylinder is going to be hotter than the room. So we're hoping that the amount of heat that it gains from the room and lost to the room, it cancels, and we could minimize that source of error. Now, if I look at this table, you'll see our temperature. The temperature of the cylinder initially is about 18 degrees Celsius. So if you look at that, right here, you can see it's going to be about 100, I think it's actually around 130 something thousand ohms. It's somewhere in there. So we're gonna start the experiment at around 230,000 ohms, 260, which is 8 degrees Celsius, and we're going to finish the experiment around 28 degrees Celsius, which is 87,022 ohms. Okay, that's the reading on the ohm meter, the ohms. Okay, so if we do that correctly, we're going to find that the heat that the cylinder gains from the room and the heat it loses to the room is going to about cancel. Okay, so we're going to try and make that happen. So let's get the experiment assembled back up and ready to run. And we're going to have to cool this down to we're going to want to cool this down to some temperature below a room temperature, around 8 degrees, roughly, okay? So in order to take it to 8 degrees, we'd have to have the resistance reading be around 230,260 ohms, okay? All right, so how are we going to cool this down to 8 degrees Celsius to start the experiment? We're going to put it we're going to get some ice and put it in some ice, but we want to put it in a bag so we don't get it wet. And yeah. All right, I'll be right back. Okay, in order to do our calculations after the experiment is over, there's a couple of things I'm going to need. I'm going to need to know roughly the radius of the cylinder. And on camera it looks a little different than by eye, but it's roughly going to be about 4.5 centimeter diameter. Okay. Which is a 2.25 centimeter radius. So we're going to need to know the mass of the cylinder. So I got a scale here. Let me zero the scale and put the cylinder on there. Looks about 202.72 grams. So those are two numbers I'm going to need as I test this equation. I'm going to need the mass of the cylinder, and I'm also going to need the radius of the cylinder, R. So I need to know M and R. The number of turns will be determined by how many times I turn the crank to raise the temperature delta T. So let's write these numbers down. The mass of the cylinder is equal to 202.72 grams, and the radius of the cylinder 2.25 centimeters. Okay? So those are numbers I'm going to need. The other number I'll need is the specific heat of aluminum, which you could look up. You can look it up online or in a book anywhere. And the specific heat of aluminum is at 0.900 joules per gram Kelvin, or gram degrees Celsius as well. So I can put in, since the size of each degree in Kelvin and Celsius is the same, per gram degrees Celsius. Okay? So that's going to, if I multiply that by a mass in grams and a change in temperature degrees Celsius, I'll get joules. And that's what's going to give me the amount of heat that goes into the aluminum cylinder by this expression right here. And we're comparing that to the actual mechanical work done and keeping it levitated as we turn the crank and the rope slips on the surface of the cylinder. Okay, so as I said, we're going to want to cool down the cylinder, and we're going to put it in this container of ice to cool it down. So we're going to put it down and put it in this plastic bag, put it in a plastic bag here, and then put it in the ice and leave it in there for a while. Leave it in there for a while to let it cool down. I can even take some, well, I can seal this bag or just tuft it up a little bit, and I can push this down into the ice more to get it embedded in the ice more and let the ice cool it down. So if I want to, I can grab some more ice and put it in there, okay, and get it packed in around it more to make sure that this gets some good thermal contact with the ice up around the cylinder, and leave it in there for a little bit, and just going to let it sit in there and get cooled down. Then when I assemble it here onto the crank, I can look at the ohm meter reading and compare that to this table to find out my starting temperature, and then do my best to just, in other words, if my starting temperature is, we already established that the beginning temperature was roughly 18 degrees Celsius. So if my starting temperature is 12 degrees Celsius, that's 6 degrees below room temp, the temperature of the room. Then I want to do the experiment till I'm up at somewhere about 6 degrees above. It'll be 24 degrees Celsius. Okay. All right. So we're just sitting here now. We're waiting for this cylinder to sit in the ice for a while, and then we'll assemble it on here onto the device and read off its temperature in ohms over there. We'll read off its resistance, and we'll convert that to ohms from the table, or to degrees Celsius from the table. So let's just let it sit in there for a while, and I'll be right back. So this has been sitting in there a while. It's a little wet, so I'm going to wipe it off. I'll wipe it off and get it a little bit dry, or dried out, and then I'll put it back on. It's nice and cold, so it's nice and cold, so I'm happy about that. Make sure the contact surface here is dry. I'll put it back on here, and then mount it back onto the experiment, okay? I'm going to mount it back on the experiment. All right, now that's back on there. And that's good and tight now. And you can see that temperature's changing here. The temperature's changing because it is colder. That's in mega ohms, at 0.252 mega ohms, which is 252 kilo ohms. And then if you come over here, it's okay, I got it. If you come over here now, 252 kilo ohms is about 6 degrees Celsius. You can see that 255 is 6 degrees, 242 is 7 degrees. So I'm going to let that get to 8 degrees, which is around 230. So when this is at 230 kilo ohms, or 0.230 mega ohms, then I'll know the temperature is at 8 degrees Celsius, roughly. You can see 8 degrees Celsius here, and I'll start the experiment. So just continue filming me, and I'll get this ready. And see, look over here. when that number is 0.230, I'm going to start turning this crank. So if you look at this, I'm wrapping the rope around it so that if you look down at the bucket, see the bucket gets lifted off the ground, and I'll put my foot under it, because once this is 0.230, look at this number. When this is 0.230, when that's 0.230, I'm going to start turning the crank. So film me from wider so you can see me turning the crank. Step back so you can see this. See the whole experiment. I'm watching. Okay, now it's 2.230, and I count the number of turns. And I'm going to keep turning this until such time that the temperature is going to be 28 degrees Celsius. So I'll just keep turning it. And I'm going to keep turning it and turning it and turning it. And when the temperature is at, so we start at 8 degrees Celsius, when the temperature is 26 degrees Celsius, or when that number over there on the ohm meter is 95,000 ohms roughly, then I'll know my experiment is done. So I'm sitting here counting turns. So step back, film me wide again, the whole experiment. Step backwards, right there. You see the bottom of the paint can? Okay, so I'm counting turns, and I'll keep doing this until the temperature is 26 degrees Celsius, which will be approximately 95,000 ohms. Okay, you can stop filming me now. You can stop now. Okay, so as you saw in my last snippet of video, I was turning the crank, and my initial temperature was a resistance of 230,260 ohms on my ohm meter, which corresponds to initial temperature 8 degrees Celsius. And my room temperature was about 18 degrees Celsius. It's cold in here. And my final temperature, I turned the crank 258 times. I turned the crank 258 times, so the number of turns is really my data, 258. Okay, and that gave me a final temperature of 28 degrees Celsius, which is a resistance of 87,022 ohms. For a total change in temperature, the initial temperature being 8 degrees Celsius, the final temperature was 20 degrees Celsius. So that's my data, and it took quite a while. It took me a long time to get the 258 turns, and let me tell you, my arm was pretty sore. Okay, so again, the theory we're testing is the mechanical work, which is mg 2 pi rn. That's the mechanical work that was done by friction on the cylinder. Is that equal to the total heat that went into the cylinder, which is measured by its change in temperature times specific heat of aluminum times the mass of the aluminum? So let's plug the numbers in on the right-hand side of this equation. The specific heat of aluminum is this 0.9 joules per gram degrees Celsius. The mass of the aluminum, as you recall, earlier we measured to be 202.72 grams. And the change in temperature is 20 degrees Celsius. So the product of those three numbers, joules per gram times grams, give me joules, grams cancel, and then degrees Celsius in the bottom cancels degrees Celsius up top. And here I am with the right-hand side of this equation being 3,648.96 joules. The left-hand side of this equation is the mechanical work done by friction from the rope slipping on the cylinder. The mass of the cylinder, again, is, this mass here is the mass of the paint can full of sand, which is 10 kilograms. Then acceleration of gravity is the 9.81 meters per second squared. 2 pi is 2 pi. R is 0.0225 meters, which is 2.25 centimeters. And the number of turns is 258. If you multiply all those numbers together, you get 3576.27 joules. Is that close to 3648.96? Yes, it is very close, and showing that the mechanical work done is roughly equal to the heat that went into the cylinder. And you can calculate the percent error and answer the questions that will be sent to you by your lab instructor. And that will be your lab report. All right, this is the final segment of this mechanical equivalent of heat video, and have a good rest of the day.